Welcome to Eugenius Panda Virtual Labs, where students and teachers access the virtual laboratory simulations for various science subjects.
Hello guys, welcome back. This video explains the concept of isotopes using a lab simulation, which is studied in Senior 4 Chemistry under Unit 1, the Atomic Structure and Mass Spectrometer, according to Rwanda Education Board curriculum. The objective of this video is to help learners to be able to define isotopes and show using a simulation the components of various isotopes and their abundances. Let's have a look at some key words. Mass number. What is mass number? Mass number is the sum of all protons and neutrons in the nucleus of a given atom. All protons and neutrons. When summed up, we get the mass number. There is also relative atomic mass, which is the average mass of all naturally occurring isotopes, calculated taking into consideration the respective abundances of each isotope. And then what is an isotope? Or what are isotopes? Isotopes are atoms which have same atomic number but with different mass numbers. They have same atomic number to mean that they have same number of protons, but they have different mass numbers because they have different numbers of neutrons. There is also the atomic number, which is the total number of protons in the nucleus of a given atom. Here we have some examples of isotopes. We have chlorine-35, for example, and chlorine-37. For a chlorine atom, we have the atomic number, which is 17, and the mass number, which may be 35. And for the other isotope, the atomic number is also 17. They have same number of protons, and 37 because they are isotopes. Remember, isotopes have different numbers of neutrons. For example, the difference here and the difference here, we get 18, and here we get 20. So this one has 18 neutrons, while this one has 20 neutrons. So isotopes have same number of protons, but they have different number of neutrons, and that is the reason why they have different mass numbers. Here we also have isotopes of hydrogen, the isotopes of boron, and the isotopes of carbon. It is very important here to note that some isotopes may occur naturally, and those are the isotopes which are considered when determining what we call the relative atomic mass, while other isotopes, which are radioisotopes, or which may be synthesized artificially, those ones are not considered when calculating or when determining the relative atomic mass. Now, let's use the simulation to see how the isotopes are related and how they are different. Here we have an isotope of hydrogen. The gray balls, these ones are neutrons. You can see the name. These are neutrons. You can remove the neutron. You can remove all neutrons, but you can also add the neutrons. You can see down here, when you add neutrons, you get what? You get the mass number changes. You see? The mass number here is changing. But even the atomic mass will also change. it decreases by 1. It is decreasing by 1. So you can determine the mass number of the isotope or the atomic mass of the isotope. Remember, every time the number of electrons is changing, you get a new isotope. Now, you can see the red ball or the orange ball. This represents the proton or protons, which have positive charges. And these ones in a blue color, it is the electron cloud. As I said earlier, the gray ones, these ones are the neutrons. Every time the number of neutrons changes, you get what? You get a new isotope. You can see this nucleus is shaking. The nuclei which will shake on the simulation when you add neutrons or when you reduce neutrons, they are the unstable isotopes. You can see here we have unstable, but when I remove one neutron, we get a stable isotope. Now let's go to the bonuses. Remember, here we are using hydrogen. We can change to have something like lithium. We have a new nuclei. What happens? You can see the mass number of lithium, which has 7 protons, can see, which has 3 protons and 4 neutrons with 3 electrons. It is a stable isotope. What happens when you remove one neutron? The mass number changes, even the number of neutrons has changed, but the proton number and the electron number, they do not change. And we also produce a stable isotope. Will it be the same if we remove another neutron? Now we have 2 neutrons, but you see the nucleus is shaking because it is unstable. Now let's go to the mixture of the isotopes and see their percentages in the nature. We have hydrogen. Hydrogen has how many isotopes? Naturally, we have 2 natural isotopes of hydrogen. And on the image here, we have a representation of the natural abundances of these isotopes. You can see the violet color, and here we have a lot of them, those ones with the violet color. We have the hydrogen color, we have a single one. Remember, the relative abundance is being represented by the number of these small balls you are seeing on the image. Looking here, we have 99.9 of hydrogen 1. And here we have 0.0115 of hydrogen 2, another isotope. So that is the natural mixture of hydrogen. This is the percentage abundance of hydrogen 1, which has no neutron, and this is the one of the isotope, which has a single neutron. You can hide this information or show it. Even here, you can hide the information or show it. What happens when you change? Let's go to fluorine, for example. You can see for fluorine, we have a single color. What does this mean? It means that fluorine has one type of atoms. All atoms of fluorine have the same number of protons and same number of neutrons. So for fluorine, we don't have isotopes. What happens when we use boron? For boron, you can say that we have green colors and the violet colors, but they are almost equal in number. And you can see that we have the green colors and the violet colors, but this time they are in big numbers. Both they are in big numbers. That is the reason, that is because boron 10 has a percentage abundance of 19.9. This is big, very significant, the violet one. And here we have 80% for boron 11 in the green. It will be present in a bigger amount, in a bigger concentration, but in the nature, but both are present in significant amounts. You can see for the atomic mass units, or the relative atomic mass, or what we call the average atomic mass, you can see that we have 10.8. It is closer to boron 11, to the mass of this isotope, which is the more abundant. So the average atomic mass is always closer to the isotopic mass of the more abundant isotope. As I said, you can hide or you can show it. You can hide or you can show it. And here, the button we have here, you can reset everything. While resetting, you can see that I have hydrogen. Now, let's use these balls. With these balls, you can make your mixture. What we have been showing is the natural mixture, but what happens when you show or when you create your mixture? If I have one hydrogen 1 and 2 atoms with a single atom of hydrogen 2, what will happen to the abundances, to the percentage composition? You can see for hydrogen 1, I have 66.7, and for hydrogen 2, I have 33.3. You can also use numbers instead of using balls. For example, for hydrogen 1, let me increase up to 6. And for hydrogen 2, I put there 3. We get the same thing, the abundances, they are the same, because we have the number of hydrogen isotopes, hydrogen 1 we have is 3 times, it is 2 times the number of hydrogen 2 particles we have. You can see here we have 1, 2, 3, 4, 5, 6. That is double of the 3 we have. You can also reduce or increase again using these buttons. Again, you can show it or you can hide it. And you can also reset. Remember, every time you don't understand something, you can pause the video or replay to get well the concept. Here we have a hydrogen isotope, H1. We have H2. Now you can see the abundances, the percentage composition is 50 and 50. You can also delete everything, the same as resetting. What happens for carbon? For carbon, let's use the nature's mix. You can see we have carbon 12, that is one isotope, and carbon 13, the second isotope, which is present in a smaller percentage composition, but this one is very abundant. And you can see the atomic mass relative, or the average atomic mass, is so close to the one which is the most abundant. You can see it here. So you can make different manipulations with this simulation, with this lab simulation, to show how different isotopes will be composed and how their abundances vary in the nature, how their abundances vary in nature, or how they will be when you make your own mixture. I hope you have understood everything very well, and I want to remind you that you can go to www.popanda.xyz to try a quiz. And here is the code for the quiz. It's VID 001-002. Here we have the steps you have to follow when taking the quiz. You go to the website, I said that. You click on login, and here it is marked with this tick. And then after clicking on login, you click on take a quiz. On take a quiz, it is here. And then you will type that code I've shown you here in this space. And then you take the quiz. I hope you have enjoyed the video and you will be there for more videos. Thank you very much.